heat and thermodynamics. We'll start with introduction, then we'll move on to thermal expansion and then calorimetry. So first we'll see what is zeroth law of thermodynamics. This law states that if an object A is in thermal equilibrium with object B and the object B is in thermal equilibrium with object C, then A is also in thermal equilibrium with object C. The zeroth law gives the basis for the temperature measurement. Now let's see what is temperature. The temperature is a physical quantity characterizing the degree of hotness or coldness of a body. If a system is in a state of thermodynamic equilibrium, all bodies constituting the system are at the same temperature. The temperature can only be measured indirectly, making use of the fact that certain physical properties of bodies change with the temperature, lending themselves to direct measurement. So we actually measure these physical properties in order to measure the temperature. So the bodies employed for this purpose are said to be thermometric. Their property indicating temperature is called thermometric property, and the temperature scale based on them is said to be empirical. Now let's see what is thermal expansion. When a body is heated, the average distance between the atoms increases. This leads to the expansion of the whole body. So we have three types of expansion. One is linear expansion, the other one is superficial expansion, and the third one is volume expansion. Now with increase in temperature, the increase in the length of an object is delta L, and the delta L will be given as L naught into alpha into delta theta, where L naught is the initial length, alpha is the coefficient of linear expansion, which is a constant, and delta theta is the temperature difference. So the change in the length, that is dl, is directly proportional to the original length L and the temperature difference delta theta or d theta. So we can write that dl is equal to alpha into L into d theta, where alpha is the coefficient of linear expansion. So from here we can write dl by L is equal to alpha d theta. And now if we integrate, say when the temperature is theta naught, the length of the rod was L naught, and when temperature increases to theta 1, the length become L. So from here we can write ln L by L naught is equal to alpha theta 1 minus theta naught, which we'll write as delta theta. So we can write ln L by L naught as 1 plus L by L naught minus 1. Now we can expand this this term, that is, this is the expression for ln 1 plus x, where x is L by L naught minus 1. So for very small temperature difference we can approximate this term to L by L naught minus 1. So L by L naught minus 1 is equal to alpha into delta theta, or L by L naught is equal to 1 plus alpha into delta theta, or L is equal to L naught plus L naught alpha delta theta. So from here we can write L minus L naught is equal to L naught alpha delta theta. Now L minus L naught is nothing but delta L. So delta L is equal to L naught alpha delta theta. Similarly, we can derive expressions for delta A and delta V, where delta A represents the change in area, delta V represents the change in volume. Here the beta is coefficient of superficial expansion, and the gamma is coefficient of volume expansion. Now we'll see what is the thermal stress. So when a rod is held between two rigid supports and the temperature is allowed to rise, the rigid supports prevent the rod from expanding. So this is the cause of a stress which is produced in the rod, which opposes the effect of the temperature change. So the effect of temperature change here is the expansion of the rod, which is opposed by the stress. The stress is called thermal stress. Now we'll see the bending of a bimetallic strip. So here is our bimetallic strip. Here we have two metal strips of equal length L and thickness delta, and both these metal strips have different coefficient of linear expansion, which is alpha 1 and alpha 2, and they are welded together. Now if we heat this system through a temperature difference of delta theta, this metallic strips bends, and the radius of bending, that is R, is equal to delta by alpha 1 minus alpha 2 into delta theta. So here as you can see that the length of the strips taken together is L, and delta is the width of the strip, and after hitting the strip there is slight bend, and the radius of bend R is given by delta by alpha 1 minus alpha 2 into delta theta. Now we'll go through the basic calorimetry. The calorimetry is based on the principle of law of conservation of energy. That is, the simple rule here is that the energy given is same as energy taken. So now we discuss the specific heat of liquids and solids. The specific heat is defined as the amount of energy required to increase the temperature of the unit mass of substances by 1 degree Celsius. So we denote this specific heat by small s, and this would be equal to dq by md theta, where dq is the amount of heat needed, and m is the mass of substance, and d theta is the temperature difference. So if we take the m kg of a substance, and we supply a heat equal to dq to it, and its temperature rises by d theta, then its specific heat will be defined as dq by md theta. The total heat capacity is the amount of heat required to increase the temperature of the entire object by 1 degree Celsius. The total heat capacity is denoted by capital C, and as it is the amount of heat required to increase the temperature of the entire object by 1 degree Celsius, it is equal to mass of the object and its specific heat, that is m into small s. Now we'll define water equivalent. Water equivalent is the amount of water when given same amount of heat shows same change in temperature. So water equivalent for a substance is the amount of water which when given the same amount of heat shows same change in temperature. Now we'll define latent heat. Latent heat is the amount of energy to change the state of unit mass of a substance. So suppose if m gram of substance requires dq amount of energy to change its state from one state to another, then the latent heat will be equal to dq by